This Zoom session is being brought to you by the fractal Almond Octaves Z forming. All right. Today, we go about vectors in space. It's a lot like yesterday's, well, excuse me, Tuesday's class. Similar ideas and fairly similar math. Okay, this is vectors in three-dimensional space. So now a vector is something pointing from an initial point to another point, to a terminal point, both in three-dimensional space. Therefore, it's a displacement with three components: an x component, a y component, and a z component, a by b by c, and it will be also noted as ai plus bj plus ck. I is the unit vector in the x direction, j is the unit vector in the y direction, and k is the unit vector in the z direction. If the vector goes from x1, y1, z1 to x2, y2, z2, then the vector has components x1, 2 minus x1, I, plus y2, y minus y1, j, plus z2 minus z1, k. So as before, it is a sum of displacements, in this case, three-dimensional space. The length of a vector, denoted by double bars of v, is done by a three-dimensional generalization of the Pythagorean formula. You take each of these components, square them, add them, take the square root. So this is a three-dimensional version of the Pythagorean theorem. Square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. As with 2D vectors, we can add, subtract, and multiply by a scalar. We do that by components. A by b by c plus d by e by f is a plus d by b plus e by c plus f. The x, y, and z components add in parallel. You subtract also in parallel. A by b by c minus d by e by f is a minus d by b minus e by c minus f, like here. And k is a number, a scalar. It determines scale or size. K times a by b by c is ka by kb by kc. So all this plus, minus, and scalar times is done component-wise. Also, like last time, there's something called a dot product. Given two vectors in space with an angle theta between them, their dot product can be gotten two ways. The algebraic definition is the sum of products of corresponding components. V1 by W1, V1 times W1 plus V2 times W2 plus V3 times W3. It's also is equal, the dot product is also equal to the length of V times the length of W times the cosine of theta, the angle between them. Therefore, cos theta is the dot product divided by the product of the lengths. V dot W divided by length of V times length of W. And theta will be the arc cosine of this ratio. Now, as before, it has dot product has various laws which resemble ordinary multiplication of numbers. Commutativity, for example, u times v equals v times v dot u. So order doesn't count. Also, distribution over vector sum. U dot v plus w is u dot v plus u dot w. It works by, so it acts a great deal like ordinary multiplication. U dot u is length of u squared. You can see that from here, if w is the same length as phi, then theta is 0 degrees and cosine theta is 1. So v dot v is length of v times length of v, or length squared. Or equivalently, v1 squared plus v2 squared plus v3 squared, and again by Pythagoras, that's the square of the length. And 0 is the vector with all components 0, 0 by 0 by 0, then going by this, it's easy enough to see that their dot product with u with 0 with v is 0. We can also talk about unit vectors. We take a vector and divide it by its length. The resulting vector points in the same direction as v, but has length 1. Therefore, it is the unit vector in the v direction. Now we have a vector pointing away from the x and y and z axes. Then it makes an angle alpha with the x-axis, beta with the y-axis, and gamma with the z-axis. And each one of those is an arc cosine. of, in this case, our cosine of v dot I over length of v. So basically we take v over length of v and dot with I, and its arc cosine is alpha. V over length of v dot j, its arc cosine is beta, and v over length of v dot k, its arc cosine is gamma. And if you work it out, that means that v is equal to its length times the unit vector cos alpha by cos beta by cos gamma. That's the unit vector in the v direction. So again, this is similar to the stuff in the previous section, generalized to 3 dimensions. And of course, you could also further generalize to 4, 5, 6, 7 infinity dimensions. But that's fairly abstract. Okay, so example. What is the distance between -1 by 2 by 3 and 0 by -2 by 1? Well, that's basically what's the length of the vector between them. Well, that is square root of the sum of the squares of the differences in components. -1 minus 0 squared, 2 minus -2 squared, 3 minus 1 squared. This will be 1 squared, which is 1. 2 minus -2 is 4, which squared is 16. 3 minus 1 squared is 2, squared is 4. Root of 1 plus 16 plus 4 is the square root of 21. Here we ask after the length of I minus j plus k. Well, I is the unit vector in the x direction, 1 by 0 by 0. J is the unit vector in the y direction, 0 by 1 by 0. K is the unit vector in the z direction, 0 by 0 by 1. 100 minus 010 plus 001. If you combine the components correspondingly, you get 1 by -1 by 1. Its length is the square root of the sum of the squares of components. 1 squared plus -1 squared plus 1 squared works out to the square root of 3. Now for these two, we're given two vectors. V is 3 by -5 by 2. W is -2 by 3 by -2. And we'll ask after what's the length of the difference and what's the difference of the lengths. Now we saw last time those are not necessarily the same. So let's proceed. The length of V minus W. So we take this minus this. 3 minus -2 by -5 minus 3 by 2 minus -2. All right, that's the length of 5 by -8 by 4. The length is root of sum of squares. So the length of 5 by -8 by 4 is root of 5 squared, which is 25, plus -8 squared, which is 16, plus 4 squared, which is 16. It's the square root of the sum, square root of 105. All right, next. Length of E minus length of W. Okay, so here, length of each one. Length of 3 by -5 by 2 minus length of W, length of -2 by 3 by -2. Length of 3 by -5 by 2 is root of 3 squared plus -5 squared plus 2 squared. Length of -2 by 3 by -2 is the square of sum of -2 squared plus 3 squared plus -2 squared. 9 plus 25 plus 4 comes up to 38. 4 plus 9 plus 4 comes out to 17. So you get root 38 minus root 17. And of course, there's no reason to expect these to be anywhere near each other. Now we're given two vectors, V and W. What's their dot product and what's the angle between them? We're getting into some trig. All right, dot product. You multiply 2 by 2 by -1 dot 1 by 2 by 3. All right, so 2 times 1 is 2, plus 2 times 2 is 4, plus -1 times 3 is -3. 2 plus 4 minus 3 is 3. So that's the dot product. The length of the angle between them is the arc cosine of the dot product over the product of the lengths. Arc cosine of dot product is 3 over. Length of 2 by 2 by -1 is root of 2 squared plus 2 squared plus 1 squared. Root of 1 by 2 by 3 is root of 1 squared plus 2 squared plus 3 squared. 2 squared is 4, plus 2 squared is 4, plus 1 squared is 1. It's 9, so square root of 9. 1 squared is 1, 2 squared is 4, 3 squared is 9, 1 plus 4 plus 9 is 14. So arc cosine of 3 over root 9, root 14. and churn it along a bit. I mean, okay, root 9 is 3, so you can cancel the 3's and get arc cosine of 1 over root 14, whatever. You get the same answer either way, approximately 74.5 degrees. Okay, that's what we have for these problems. Okay, I believe we've